Okay, so going through these answers then. So on the first one here, first thing you do is complete this frequency table. So we've got the 1825 missing, we've got the 25 to 40 missing. Now we can see that if we just simply do the class width times the frequency density, we get the frequency. So if you just look at that 14 to 18 group, for example, you know it's got a width of 4, a height of 6 there, and we get 24 as our frequency. So we know that we haven't got to adjust it, which we have to do in the second question. So firstly then, you've got a width of 7, a height of 5, so that's going to be 35. And then the second one, you're just going to get 15, okay? Width of 15, height of 1. Can you just put your hands up if you got 35? And put your hands up if you got 15. Okay, just make sure that it might have been a little bit, it might have possibly been the height didn't maybe look like it lined up with 1. Yeah, just be 15 there. Okay, so the next one of the swimmers claims that over half the swimmers take longer than 20 minutes to swim 500 meters. So investigate this claim. So this is going to be part of the 18 to 25 group. So you can do this a number of ways. You can just still work with the areas, which probably is the way most people have attempted this. So just look at the width being 5, the height being 5 as well. So you do 5 times 5, the 25, and then we add on the 25 to 40 group as well. So don't forget to do that. So you should have 40 swimmers here. Total number of swimmers is 100. So then if we're comparing a half, we want to compare this in proportion. So then we need to do a little calculation to justify it. Okay, so just working out that there's 40 isn't good enough. Okay, it will get you some credit, but it won't get you all the credit. So you need to make sure you work out some sort of fraction that you can compare with, or a percentage. Percentages are often better to compare than fractions, because with fractions you can have different denominators. So that's why the percentages are better a lot of the time, or decimals. So 40%, which is obviously less than half, which is less than 50%. So therefore, the claim is incorrect. We could technically argue that because we don't know how the data's spread, that there is potential that all of the people in the 18 to 25 group all took over 20 minutes. So there is a potential to argue that it is actually exactly half. Well, it could be, exactly half. If the data wasn't evenly distributed, but we'd assume that it is. So for our estimate, 40%, it's highly unlikely that it's going to be that they all took, all 35 of them took 20 minutes or more out of that 18-25 group. Okay, so you just put your hands up if you got 40%, or you might have done it some different way. Does anyone do it a different way, or? Okay, right, what we'll do then is we'll go on to the next one then. So, in this one, so I slightly changed this question. Originally, it was a little bit easier with the scale that was given, so I've just changed it to make it a little bit more tricky, because sometimes you might just get given a graph here, well, histogram here, without frequency density on there. So you need to figure out what it would be. So you get told that there's 1,600 apples altogether. So what you need to do is, and there'll be different approaches. So I've done it one particular way. I've seen there's gone around some other ways which are perfectly valid. So you can either just kind of look at the widths of these, which is what I've done, is just said, well, going 20 to 40, that's the class width of 20, and then just times it by the height of how many squares we're going up by. So that's the way I've done it. But if you also notice, if you actually count the squares, it's not actually 20 squares between 20 and 40, is it? Because it's going across in twos. So you might just do 10 times the height of 7 as well. That's fine. as long as what you do is you work out using that scale, does that give you the 1,600? If it doesn't, then you need to adjust what that height is on the for the frequency density. So the way I did it was, as I mentioned, looked at the width. So between 20 and 40, you get 20, and you've got a height of 7 for the first bar. So I said that has an area of 140, and then the next bar, 10 across, 17 up, so it's got an area of 170. So that's what I did. But if you did the method where you counted the number of squares, you would have got 400, which is absolutely fine. Okay, so you can do it that way as well. Remember, histograms, it all works in proportion. So you can take different methods to use different methods to do this. So if I've got 800, I need this to make 1,600. So instead of counting 1 every time I go up, I need to count 2 every time I go up. Or just simply put, if I work out an area, I need to double it, the way I've done it. If you're doing it with this, counting how many little squares, and you've got 400, what that tells you is that each little square is worth a frequency of 4. Okay, so yeah, again, you can do that way as well if you just count with the squares. So between 20 and 40, the area is 140, so the frequency is 280. If you've done it by counting the squares, you would have counted 70 squares. Each square is worth 4. 70 times 4 is 280. So you either way, you should get the same frequency, regardless if you have a different area. And then between 40 and 44, so using my method, I get 68 as the area, so the frequency is 136. Then we simply add them together for 416. Could you just put your hands up if you've got 416? Okay, very good, excellent. Okay, it's quite a tough question that, so well done if you got that final answer there. Final question then. So I haven't drawn the cumulative frequency graph for this, but that's the method that you want to take. Okay, think about what the box plot shows you. It shows you the lowest and highest values. It shows you lower quartile. It shows you upper quartile. It also shows you the median as well. The second set of data is in a frequency table. Now, I can do quite a few things with this. I can find the mean. I could find the standard deviation, for example. However, I can't compare median with mean. I can't compare interquartile range with standard deviation. So therefore, what I need to do is plot a cumulative frequency graph so I can compare the two pieces of data. But before we get into that, the first question says, Lisa says the lightest lamp came from the Scottish mountain sheep. Explain why she may not necessarily be correct. So any reason why she might not be correct there? Yep, Dominic? Yeah, so you know it's 2.2 for the Welsh ones, okay, but you don't know. You know it's between 2 and 2.5, so it could be in that group. It's not wrong that it's not definitely wrong to say it could be in that group, but we're not sure. Okay, we're not certain on it. Okay, it could be anywhere. The lightest one could be anywhere between 2 and 2.5. I will say, by the way, I got this question and then kind of added this next bit. So obviously Welsh mountain sheep is a thing. I have no idea if there's such things as Scottish mountain sheep, so I just made that up. I just assumed if there's a Welsh mountain sheep, there might be Scottish ones as well. Who knows? So when we're comparing our weights for the next bit then, so we plot our cumulative frequency graph. So we compare the median and interquartile range. Now I haven't plotted that graph, okay, but I've on here, but I can show you the rough values that I get when I've done it. Now your values may differ than what I've got here, but I think what does make it easy is you've just kind of put everything in a nice little table like this. It shows all your key numbers, For an examiner, it makes it easy just to see where everything's coming from. It presents all the information nicely, and you can easily make that, and also for yourself, you can easily make those comparisons. So I did put there 2 for lowest and 5 for max for the Scottish. We don't know that for sure. Okay, so we don't know that for sure. But that's the absolute kind of maximum it could be, and the absolute lowest it could be. It most certainly couldn't be anything lower than that. It most certainly couldn't be anything max for that, for the Scottish sheep. So with that all on the table, the 2 key things that we're comparing here are the medians and the interquartile ranges. But we can also make comments about lowest and max values as well. So for median, we can see the Scottish ones are slightly lighter, so we can say the Welsh lambs are heavier as the median is higher. So make that point, back it up with your evidence. You could also say the Scottish lambs are lighter as the median is lower, so you can say that statement in the opposite way. Then the weights of the Scottish lambs are more inconsistent, or they're more spread, as the interquartile range is higher. So again, these are the values I get. Yours may differ. Okay, so you probably might get anything from like 0.9 to 1.3 for your interquartile range there. Anything within that range sounds sensible. The only thing I would say should definitely be the value I've got here is for the upper quartile, you should definitely have 4. Just because you actually plot it bang on the 60, which is at the end of that 3.5 to 4 group. So you should definitely have 4 for your upper quartile. Obviously make sure that you plot the upper bounds here when you're doing your Coombs-Fuchs graph. And you could also then say, with confidence, the Welsh group contained the heaviest lamb. Whereas you can't say with confidence which group had the which had the lightest lamb. You can say for certain that the Welsh group contained the heaviest lamb, because the heaviest for the Welsh ones were 5.5, whereas there was no Scottish one that exceeded 5. So you can say with confidence that the heaviest lamb was in the Welsh group. Okay, any questions there? So when all of the data is collected from a population, this is called a
just one, there's still one.
Oh, they're not doing it. Okay, so census, good. Okay, Fran lazy at the moment. So what is a disadvantage of the mean? It's not doing it. Sorry. If you just like, right, you can just write the answers down as you go along. You always try and log back out and try and log back in. So the weights of cats collected, what type of data is this? Remember, weight is going to be continuous because you could be, the cat could be anything between 4 and 5 kilograms. Okay, obviously when you measure it, you're going to round it to certain numbers, but it could be anything between the 4 and the 5. That was my cat, by the way. Just thought I'd point that out. Yeah. So if the standard deviation of a set of data is higher than another, what does that mean? Whoops, sorry. Press red, I'm sorry. Sorry. That was my fault. I think I meant to put it's less consistent, sorry. Whoops, sorry about that. I was supposed to put less, sorry. I know that's probably ruined everything now.
Yep.
Maybe we won't go that far. So the town's chosen and the sample is taken from that town about shopping habits in the UK. What type of sampling is that? Yeah, cluster sampling. That is right.
Wait, how many people is there in this? If you tell me there's 10. There's 11. Oh my god.
So cluster, so you treat each town as a, so basically each town would be a cluster, okay? Tom? So each town would be a cluster in this example. So that's why it's cluster sampling. So the sampling method in the last question may be biased because if you can't see the ones at the bottom, the socio-economic background may be different to other towns. Bottom left, bottom right, any type of sampling has an element of bias. Top left, different towns are different sizes. Top right, people may lie. So it wouldn't necessarily matter about the size of the towns because that's just going to be the sample you take. But if you're looking at shopping habits, you know, if you go to some kind of posh bit of London, for example, it's probably going to be different to other towns that might not be as well off. So that's why you'd have to be careful with that sampling method, because a town, if you look at the whole UK, looking at just one town is likely to be quite different. So you're not getting the full picture. It wouldn't be representative.
I'm so mad. How did you guess it right even before the answers?
Still got it wrong, red green.
Guessing isn't the best strategy here, because you get like.
It worked then, though.
Yeah, but it didn't though, because you pressed the wrong one.
Yeah, I still got the right answer.
So if you thought about it, which of these is not a valid way of obtaining random numbers?
We both have to use.
No, you can use a spreadsheet. A spreadsheet can generate random numbers. If you're in Excel, you can just type in. There's a function that just generates random numbers for you. Getting your friend to think of some numbers is not a valid method, because if you think about it, you know you're not going to be as kind of efficient as a computer in being truly random. Okay, because what we'll naturally do. No, some people will think, well, I'm not going to say 1, I'm not going to say the max number, I'm going to say a lot of numbers in the middle. Okay, or you might think, well, I've already said that one, I can't say that again, whereas a computer won't care what it's previously done, it will do something truly random next time. Okay.
I want like late charge from 10.
And then last one then is stratify. So you need calculators for this one probably. Okay, that came up smaller than I thought. I'll write that bigger if you need that. 90.
Why was that 28?
and a B2.
That's right.
Sorry, I thought that was going to come up a little bit.
Let's go for 15.
I think I've done it wrong.
I get it.
I've guessed it right.
Nope. You are, yeah, I did. Yeah, you get it, yes, it's 50% one of our thoughts.
I want to just guess what already we said before. Got it.
So, with this, we need to think about how many. So you've got 80 of the year 13s are male, so you have 80 out of 400 overall. So if a fifth of the group are year 13 males, you need to make sure in your sample you have a fifth of year 13 males as well. So if you do a fifth of 60, or just 80 over 400 of 60, you're going to get 12. Okay, so that stratified sampling, remember, it has to be reflective of the population. So, apologies for the little mistake that was in there. I kind of looked at it, I was like, oh no, that's not right. So sorry about that. So sorry, this might not be quite the same as it should have been.
Oh, yes.
It's not really.
So well done, and I'm sure that would have been 9 out of 9 if it wasn't for the one about standard deviation. So of course, standard deviation does standard deviation. Obviously, the higher the standard deviation is, the less consistent the data is. But at least you all did spot that it was wrong. You know, you didn't kind of blindly go,